Hi everyone. Welcome to the third video in Lecture 7. In the last two videos, we introduced a lot of concepts from differential geometry, including manifolds, vectors, vector fields, and some ways that we can do calculus in this sort of new setting. We talk about coordinate transformations and the freedom to work in different coordinate systems and change between them when we need to. In this lecture, we're going to talk about one-forms, which are going to give us a lot of powerful machinery that we'll use in the next few lectures. Okay, so let's try and introduce this subject from the beginning. So we talked about the possibility of having some manifold gamma and a point x in gamma, and then the fact that we have a distinguished copy, or maybe not a distinguished copy, I should say, but just a copy of the vector space Rn, if this is in Rn. So we have a copy of Rn living at x that we call T sub x of gamma, which is called the tangent space at gamma. So anytime we have a vector space, we can define this set of so-called dual vectors. You're probably familiar with this already from a linear algebra course. If we have a column vector, say 1, 4, 7, then we can construct a row vector, say 2, 3, 5, of the same size. And we know that when we multiply the column vector on the right by a row vector on the left, we get just a number. So this is just a real number in this case. And we can even evaluate it. The way we do that is we just go term by term, right? So 2 times 1 plus 3 times 4 plus 5 times 7. So in this case, we would get 2 plus 12 plus 35, or 49. Okay, so the key is that we have some linear function on the vector space that takes it to the real numbers. So what we want is the space of linear functions from Tx of gamma to the reals. In math, we have a name for this space, which is, again, the space of dual vectors or the dual space. Sometimes it's called the space of covectors. We'll denote it by T star sub x of gamma. And it's called the cotangent space. Now, another thing we know about dual vector spaces, so you could think of the space of row vectors, is that given any basis, we can come up with a dual basis. So suppose we have a vector space, let's call it W, with basis E sub I. Then W star, the space of dual vectors, has a basis which we often denote E sub upper j, and it satisfies the following. Let's say satisfying E sub j, or sorry, E super j of E sub I. Again, we're going to use square brackets for this natural action, but you can just think of this as a row vector multiplying a column vector, is equal to the Kronecker delta I j. Good. And this is always true. So we will have one of these bases, sorry, for the cotangent space. And we should probably denote it. So we'll denote the dual basis to the coordinate basis, dAI, by d, and we'll use this symbol here, lowercase d, AI I. Okay, and we know that we have some natural action. In fact, let me use J here instead. dAj, which acts on, partial AI, and this is the Kronecker delta. Wonderful. Okay, so now we have this notion of these things, and we can put them together. So a covector at x has the form, and let's say a covector omega has the form omega is equal to, well, we can write it just like we did for vectors, except the indices change whether or not they're superscripted or subscripted. So we'd have omega sub a, let's say 1, dA1 plus omega sub a2, dA2, and let's just imagine we have 2. Or we could write this using our Einstein summation notation in this way. Good. Now we know how to act on a vector v. So omega acting on v will be as follows. So let's just rewrite what we had above. And now we're going to have it act on v, which we can say is VAI partial AI, where the addition over these partials is implied. Now remember that covectors act on the partial derivatives. They act on the basis vectors. These are just, well, for us, they're just numbers. And so they can come out of this action since it's linear. So we'll get omega aj VAI dAj partial AI. But we already know that this is the Kronecker delta. So this leads us to the expression and finally, because we're summing over this, we can, for instance, sum here. This sum is only going to have one non-zero term, which is the term where I is equal to j. So at last, we can say that this is omega aj VAj, where the sum over j is implied. Good. Okay, the next notion that we need to introduce is the notion of a one form. So just as we had vector fields, which were maps from every point on gamma to the tangent space at that point, we can have covector fields. A covector field on gamma is called a one form. And one forms will be extremely important to us as we continue our study here. Now, the next concept to introduce is the notion of the exterior derivative. Now, this object generalizes the gradient. As you know from any multivariable calc class, the gradient is an extremely important operator. It allows us to say something about all of the partial derivatives of a function in every direction all at once. And the exterior derivative is going to allow us to do the same thing. Okay, so what is this thing? The object is called, or is denoted by D. And for now, let's say that it's a map from the functions on gamma to one forms on gamma. Okay, and this makes sense given what the gradient is, since the gradient acts on functions. And it makes sense if we say that one forms on gamma somehow have something to do with partial derivatives of somehow have something to do with partial derivatives. Sorry, let me back up. Okay, so this object is denoted D, and it's a map from the functions on gamma to the one forms on gamma. So let's remember what the gradient does. It's going to take a function in and output somehow all of the partial derivatives of the function. That means that the one forms on gamma should have something to do with partial derivatives in some way. And we'll see how that works out in a second. Okay, so let's have D act on a function. So I'm to think that this is a one form. But if it's a one form, then at any point on gamma, it should be expandable in the basis. So how do we expand it in dA1, dA2? The answer is as follows. dF is equal to the partial of f with respect to a1, dA1, plus the partial of f with respect to a2, dA2. Good. Okay, we can also write that using our Einstein summation notation as the partial with respect to aj of f daj. Okay, so just as promised, this object includes within it all of the information about the partial derivatives of f with respect to the coordinates, and they're separated or kept sort of distinct by the fact that they're attached to these basis elements. Good. Okay. Now what we have left to do is show why we might be able to use this in a number of ways. So the first is that it encodes all of this information about partial derivatives, so it gives us a way to keep track of things. The second is that it is going to allow us to do coordinate transformations. So let's look at that. So suppose again that I have df, or actually let's even be more general. Suppose that I have omega, and omega is equal to omega aj daj. And I want to transform this into the coordinate system bk, let's say. Okay, so just like for vectors, I need to know how the covectors transform. And again, just like for vectors, we're going to use something that kind of looks like the chain rule in order to do it. So what we're going to have is we're going to just rewrite this omega sub aj, and then we're going to write daj, but think of it as a function of b1 and b2. Now, because we know how to act by this operator on functions, we can expand this in terms of b1 and b2. So this is going to be equal to omega sub aj partial bk aj dbk. Good. Okay, now an exercise that you should attempt for yourself is to check that omega acting on v is the same evaluated in two different coordinate systems. Which it should be, because the vector and the covector haven't changed at all. We've just changed the coordinates in which we evaluate them. But if you check on this and use the version of the inverse function theorem that we saw last time, you'll see that this is in fact true. Wonderful. There's one other important property that we need to talk about for D, which is that D satisfies the product rule. Again, this is just like the gradient. Okay, so what do I mean by that? Well, d of f times g, if f and g are both functions, is equal to g df plus f dg. We could, of course, go and check that, and it would follow from the fact that partial derivatives themselves respect the product rule, but I'll leave that for you to try if you'd like. Now let's use everything that we've shown here in order to make some progress on thermal physics. Okay, so what I want to do is look at ds, where S is the entropy of some system. And just for simplicity, let's assume that we have a gas system. With internal energy work coordinates UVN. Okay, so let's expand this in the internal energy work coordinates. So we'll get that ds is, well, it's going to be the partial with respect to u while fixing v and n times du plus the partial with respect to v of s fixing u and n dv plus the partial with respect to n of s while fixing u and v times dn. You'll notice I've switched back to our other notation here, where we do keep track of which variables are fixed at any time. I think that makes this a little bit easier, but you'll see that it is totally coherent with what we've said before. Okay, the key here is that we know what all of these quantities are. This is 1 over the temperature. We've encountered it before. This, is the pressure over the temperature. And this is minus the chemical potential over the temperature. Now, looking at all of the expressions on the right-hand side of this equation, it makes sense to multiply both of the sides of the equation here by t. If we do that, we then get T ds is equal to du plus P dv minus mu dn. And you'll often see this written in another way, where u is left on one side of the equation by itself. So let's do that. Du is equal to T ds minus P dv plus mu dn. And this is actually another version of the first law of thermodynamics. Now we'll justify that in the next lecture, but let me give some evidence about why it might be true. Somehow these one forms have to do with the gradient. They have to do with what happens when you move in a particular direction. So if we imagine moving along some curve, it seems to be the case that this is going to tell us about how u changes, and this is going to tell us about how some other things change. So it turns out that all of the things on the right-hand side of the equation break up into the different ways that a system can gain or lose energy. In particular, for reasons that again will become clear in the next lecture, this one form, T times ds, is called the infinitesimal heat form. This is called the infinitesimal work form, and we'll be more specific even. We'll call it V work form. And then similarly, this would be the infinitesimal N work form. And we can be a little bit more general here as well. OneNote has decided to stop working. One moment. You can check that if we do this for a system with general internal energy and work coordinates, we'll get du is equal to TdS plus the sum over J of the J pressure times dVj, where Vj is the jth work coordinate. And so again, this would be the infinitesimal heat form. And each of these would be an infinitesimal work form for Vj. In the next lecture, we'll see how this has to do with what happens when we move the system around its state space quasi-statically. Until then, I'll say thank you so much for watching, and I'll see you in the next video.